Good morning, everyone, or good afternoon or good evening, depending on where you are. Welcome to session 6, the final session of the foundational statistics for forensic toxicologists. My panelists are here today as we walk through some of the questions we've received from various sessions that you have seen previously, and to field your questions today that come in live. So feel free to go in the question and answer pod. If you get your question in early, you have a more likely chance of getting them answered. And we'll be going through some basic questions that we've gotten throughout the series. I encourage everyone to answer your questions. This is your opportunity. If you feel for whatever reason a little shy about asking a question and you don't want to put your name out there, feel free to go anonymous, but please ask your questions. That's what my subject matter experts are here for. They want to hear your questions. I promise they're very gentle. They have been with me with all of my questions for sure, and I greatly appreciate both of them. So we just want to encourage you to ask some questions, and we're going to start off today's talk with, you'll be able to see our faces for most of the time. And we're just going to start off with some very basic introduction things that people had asked, mainly about Brigitte's presentation that she gave. So someone had asked about her TF podcast that she gives. She has an entire stat series that she gave, and they wanted to know if non-TF members were going to be able to access it. So Brigitte is about to get an explosion of emails into her email account. Brigitte, please add mine on there as well. I would love to have access.
Yeah, it's not so it's not a podcast though, right?
Oh,
It's a series of papers.
I know you've been on their podcast before as well, though.
Yes.
So yeah. Yes. So Brigitte's contact will also be at the end. It's also included as part of the a part of the documentation for the website. So you can always get it there. You don't have to scribble it down really quick. But go ahead, Brigitte. Do you have something to say about your publication?
Yeah, no, I mean, just send me an email and I will send you a link. So it's just like any other scientific publication. I can't really put the link here and just share it, with everyone. But if you send me an email, I will send you the publication, no problem. So,
Well, that's great.
And
And thank you
and
for
if you get an automated answer saying I'm on mat leave, that's true, but I will answer your email still. So
Yes, for sure. So thank you for that opportunity for everyone. And thank you for asking the question, whoever did that earlier in the session. Just for a little housekeeping, just so you know, I'm going to be looking off camera a little bit as I monitor the chat and the pod as well, so that I can facilitate some question and answers. So we already have a couple of questions in the Q&A section, so please ask them. I'm also going to be active in the chat section, maybe prompting a couple of questions and getting some feedback from you guys. This is an opportunity for all of us as a community to learn from each other as well, what we also do. So our next slide up here is also a question from a previous session. We're just going to have some warm-up slides while everyone starts getting in the groove here. And so this is some of the introductory resources for R that I believe Brigitte also spoke about these as well. Did you want to take us through a little bit of this as well, Brigitte?
Right. So I don't think I spoke about these specifically because I didn't want to get too much in R versus Excel and like try and convince people to go over to R. But for those that are interested, here are a few introductory resources, and they're all free. So R is a coding language, and you have a user-friendly interface, which is RStudio, that you can both install on your computer, and both are free, and it's open source software. So it means that there is actually a lot of resources that are online, and they're online for free. And you can pretty much Google everything and come up with an answer because there's a really wide community of users. So just a few resources, and R bootcamp if you want to start coding in R, And you have a lot of books from O'Reilly or CRC Press that are really good resources for R and that are free. And so the one here is R for Data Science is sort of a basic one just to get started in analyzing data in R. But you have so much more books that are free, and they're sort of all tabulated in this big book of R website. So if you're looking for a specific subject, you can go in this link, and it sort of lists all of these free books that are available. So yeah, just a few resources.
Excellent. That'll be great. And we'll probably add this to our list of resources as well that people may have access to in the RTI website as well. So in the interest of kicking off some questions and getting the chat warmed up and getting the speakers warmed up and comfortable, we're going to launch into our first kind of discussion period, which is what is the difference between accuracy and bias? And we're going to let our subject matter experts chime in on that particular question. And if you have a question, please ask it. If it concerns accuracy and bias, I certainly will try to work it in during this particular session as we do this type of discussion between accuracy, the term accuracy, and bias and what they actually are. We'll kind of shore that up a little bit. So go ahead.
Hey, Ariana, I want to just take the time to also introduce Dave Heller from RTI. I can't call him our resident statistician because he's not ours. He's actually RTI statistician, but he's been along with us throughout this series to provide some support and also just statistical encouragement that we're not, going down the wrong path with any of our understandings here. And so, Dave, feel free to chime in as you see fit. But I think to start with this question, Brigitte, you had kind of prepared at least an update. I think it's a question that comes up a lot. And as standards are written, as you look through textbooks and resources and hear presentations, we hear both terms, right? So how are they different? How are they the same? And what did the ASB working group have to say about it?
Yeah, so this one's actually funny because Arya in her presentation said, oh, accuracy, bias. Oh, funnily enough, the ASB standard only mentions bias. And I thought this was funny because I'm part of the panel that's working on the second edition of the ASB 36 standard, so the method validation standard. And just like weeks before, we'd gone over this question of, oh, should we be using accuracy or bias? And I was like, you know what? This has been bugging me for like years now, and I'm gonna I'm gonna get the answer to this question and put a final,
get to the bottom of it.
Yeah, let's get to the bottom of it, exactly. And so it turns out that, okay, so bias is the difference between the value that we wish to estimate, so the true average or the true value, and the average of the measured values over a large number of samples. So that's the X bar, right? It's the mean of the samples that you've measured. So it's the difference between the target and what you've measured. So you can go to the next slide. So accuracy, bias in the statistics literature, very well defined, and pretty much everybody agrees on what it is. Accuracy is a bit more debated and fuzzy in the stats literature, but the majority of the sources, they define accuracy as the average quadratic error. Okay, so what is the average quadratic error? I mean, suppose you have 3 QC levels. Accuracy would be, the QC1 measured minus QC1 expected, and you square this difference. And you do that for QC1, QC2, QC3, and you take the average of that. Okay, so that would be accuracy. And so if you go to the next slide, you can show that this formula, it's actually equivalent to taking the square of the bias and adding the variance. So that's why you're going to read in some sources that accuracy encompasses both bias and precision. It's because it's equivalent to bias squared plus variance. So what we're targeting in method validation, it's really bias, right? we're not interested in the square of the bias plus the variance. What we're targeting is the difference between the true value and the measured value. So what we are really after is bias, and so that's why bias is used in this standard and will keep being used in will keep being, anyways, my verb tenses are all over the place, but that's what is going to be used in the next edition of the standard is bias. So I think this is really an instance of a misnomer, that when we say accuracy, we're not really thinking bias plus variance or bias squared plus variance. We're really thinking about the bias, so it's just a misnomer. So really the term we should be using is bias.
Yeah, is it safe to say that the term or our understanding, or maybe the layperson understanding of the phrase accuracy is what we're often talking about when we talk about it, right? We're talking about bias as a way to describe the general accuracy. We're not thinking the formula, we're not thinking, bias squared plus variance. We're not even thinking about a calculation necessarily when we use the term accuracy. And so to be specific, right, that calculation and that statistic is the one that we're interested in is bias, but we often talk about accuracy. And I think, don't jump down people's throats if they start using the word accuracy in place of bias. I think it's just the awareness that we use the term for maybe a broader definition as a measure of its trueness rather than the actual calculation. And this reminds me of, I think it was in session 2 where, I had put up these terms that like what we hear in forensic stats, I'm sorry, what we hear in stats and then what we hear in forensic talks, we use a lot of the same words, but what we mean is quite different. And here's an example of that too, right? That accuracy is just, we're talking about it more broadly and maybe not using it inappropriately, but especially in a national standard, it is important that we're
I agree. And I mean, I've used accuracy as well when, that's what we still have in our documentation in our lab, and they're going to have to change it. Oops. But so, I mean, I've used it as well, and I think you're right that that's what people have in mind. But yeah, as we go forward and refine standard and refine papers and vocabulary, then we can do this sort of adjustment between the terms throughout the different disciplines so that there's no confusion when we're talking to one another.
Yeah, that's a really good point, especially across disciplines as well. Okay, so I have a couple of questions from our pod here that I think before we get into the next session, into the next section, we can probably hit some of these. So we have a question that says, if we assume that the percent CV of an assay is 10%, so the percent CV of an assay is 10%, is the 95% confidence interval plus or minus 20%? Or 2 standard deviations? And I'm going to copy these into the panelist chat so that you can read them at the same time.
Yeah, let me think out loud here. Assume the CV of an assay is 10%, right? So that's a standard deviation divided by the mean. So the variation of the method is 10% of what it is describing. So whatever that value is the 95% confidence interval plus or minus 20%. I don't know that these two things are directly related. Brigitte, you want to jump in?
Well, okay. So if we assume that this is a normal distribution, I think that this is what this is stating is sort of a rule of thumb, right? That if you have a normal distribution, you can take 2 times your standard deviation, and it's approximately your 95% confidence interval. But that so it's a rule of thumb, right? But it doesn't take into account how many how many replicates is your standard deviation based on, right? Because if it's based on like 3 replicates, then you sort of have to adjust the K factor or the 2 to. So anyways, yeah, like the factor, the multiplicating factor, the coverage factor that you use, if you have a low number of replicates, it's going to change, it's going to increase, basically. So I think that this is a good rule of thumb that, it's going to be approximately, your 95% confidence interval is going to be approximately 2 standard deviations. But it depends on the particular circumstances.
Yeah, and maybe the question asker is kind of alluding to the fact that is the relationship between 10% of a CV, if you multiply it by 2, is it representative of 2 SD, right? And that's the part that you're saying, like, assumes normality and sufficient data to make that, right? If you've got less data than that, it might actually represent less than 2 SD. It might be, 1.5 SD, even at 20%. Because that expansion factor is not 1 and the same as 2 based on your sample size.
And so going along with this confidence interval, we have another question, which is why are many of the statistics reported with a confidence interval of K equals 2 with a 95%, when there is a stronger K equals 3, 99.7% available to use? Like, what would be the preference of K equals 2 versus using a K equals 3?
This one is a fun one.
Yeah. I would agree. Go ahead, you start.
Okay. So my answer to that, especially when we were discussing, measurement uncertainty in the lab, is, well, if you want 100% confidence of where, my sister is today, I can say the universe. But it's not a really helpful thing that I'm telling you right now. 95% confidence, I can tell you, well, she's probably at home, 95% confident, right? And this is a more useful piece of information than the universe. That's something you can act on. And it's sort of the same thing with confidence interval, that if you want a 100% confidence interval, it's going to be like, well, minus infinity to plus infinity. And if you have a 99.99, it's going to be still really big. And, as you drop in confidence, the interval sort of shrinks. And so, yeah, maybe it's used more actionable as a data thing to have a more reduced confidence level, but a more reduced confidence interval as well.
All right.
I've got absolutely nothing to add to that. You couldn't have said it better. I think
I would agree. Okay, so along the lines of some of this, so the question is, when assessing the real case results from a batch, if the quantitation of controls are all within an acceptance criteria, let's talk about the plus or minus 20%, what does this tell me about the accuracy of the case results, the one case analyzed once in a batch? Does this case result have uncertainties? And we may cover this.
Let me read through it, read in between the lines a little bit. I think what the question is really asking, right? I think there's 2 things here. One is, how do QCs inform us about the accuracy of the measurement? Right, that's one question. And then the second part of this is, like, does each case result, does each unknown have its own uncertainty? Right. And I think I'll start with the latter one, because I think it addresses measurement uncertainty, kind of finish off that conversation. Does each case result have an uncertainty? The reality is we're making one measurement, right? We have that material and we test it one time. Even if you test it 2 times, you're not testing it 1,000 times, and nobody really knows the true value. So you're making your best estimation, you're making a measurement given a validated method, right? With proper controls in place, proper quality assurance, to try to characterize what the concentration of whatever drug is in this particular case sample. So inherently, a measurement process has uncertainties, right? The starting material that you use, the equipment, the sample extraction, the calibration curve you prepare, all this stuff contributes to the uncertainty or the potential variability if you were to test that case sample multiple times, you're going to get slightly different results, right? That's about the measurement process. To answer the question narrowly of like, does each case result have uncertainty? I think that's kind of a philosophical question. I would say like, no, because the true value has no error. The true value has no uncertainty. The true value is what the true value is, but we don't know what that is. That's the whole point of measurement, right? Is to try to characterize that. Mm-hmm. Before we switch to the other question, any comments, questions about that?
I don't have any, but I think this is a great segue into a little bit of our next section of talks, which is about how do you phrase measurement uncertainty in court? And I would love to hear from people in the chat. Just kind of give us a little blurb about your canned statement to your juries that you kind of use to explain measurement uncertainty. Just throw them in there. We have some examples too, trust me. But we're going to go through for a few minutes and kind of cover, you know, what is that statement that you train your people to say when they're in court. That's kind of short and sweet. And then we'll kind of discuss it a little bit like we did yesterday going through this. I learned quite a bit. So we can start kicking that off a little bit and get that started on how do you phrase what measurement uncertainty is for court?
So while folks are deciding if they're brave enough to put it in the chat, I'm going to start with this to say that this is something that I've heard before, right? A statement like this, we're 95% confident that if we were to test the sample again, the result would be between whatever that lower bound and the upper bound is, with the most likely result falling close to the original result obtained. So I've heard it said this way, right? 95% confident that if we tested it again, it would be between whatever those two values are, right? That range, with the most likely result falling close to the original result. So I'll put it to our panelists, including you, Aria, and Brigitte, you know, is this an accurate statement? What do you think about this?
So I think that there's a bit of language slip here. And that if we're being really strict about it, it's not an accurate statement. And the slight slip that I'm seeing here is that it says the result would be between the lower and upper boundary of the confidence interval that we've measured for this unknown sample, but that's not really how confidence intervals work. So how confidence interval works is that if I were to build 100 different confidence intervals, so if I were to measure 100 different times my sample and build confidence intervals for these 100 measurements, 95 of them would contain the true value, right? But we don't know what the true value is, but we know that 95 of them would contain the true value. And so that's where the slip is here, is that it says that 95% of the, well, it's a probability statement, and then it also says that it's 95%, it hints that 95% of the result would be between the lower and upper boundary that you've calculated for an unknown, which is not the case. So anyways, there's different language slips in I think in this phrasing here.
All right, do you want to add anything?
Yeah, I mean, after our discussion yesterday, I also had my eyes opened as to the differences between assuming the normal distribution and trying to explain that from a single measurement. That is how you generate measurement uncertainty, for sure. But now we're applying that range to a single measurement that we don't know where it is. So I definitely have learned a lot. We had someone in the chat say that their statement for court is that that the measurement uncertainty attempts to encompass the true result within a determined range. So, I mean, it's a nice short and sweet, I think, as well. But Sue, what did you have to say about this particular statement?
Yeah, I think what Brigitte said, and Aria, I like how you put it, right? That the normal distribution and the tails that we're kind of envisioning of that normal plot is the foundation to determining the measurement uncertainty, right? We use that to calculate it. However, what we end up with at the end of that process is a test result and the measurement uncertainty of that. And that confidence interval, the distribution in that range, is not something that we've described. But I can see how you can easily make that jump, but that's like the minor language slip that Brigitte is talking about. And I think sometimes we can get really caught up in the language of this. So I would stick with something that is simple enough, that is true, that you fully understand. And if more information is needed, you can always explain more. But I think the critical part is that the knowledge is really there. So let me put up a slightly different example. This top statement says, if I were to test 100 times, right? So I was going to test the sample 100 times, only 5 results would be outside of that lower and upper boundary. That's something that I've heard as well, right? Similar concept, you have a range and only 5% of the time you'd be outside of that range. But notice the slightly different language in this rewrite. If I were to build 100 confidence intervals, only 5 of them would not contain the true value. And that's a distinction that Brigitte was trying to make, right? That what we're talking about is not the individual results being outside of that boundary, but that boundary that you made, that confidence interval that you create, if you replicated that 100 times, only 5 of them would not contain the true value, right? I think the first statement kind of implies that 5% of the time you'd be making a mistake and that the value that you got the first time is the true value. And we don't know that to be true, right? It's a very, very slight nuance, but however you phrase it, right, to be able to fully understand and make sure you're not saying the wrong thing. Now, we were talking about this a little bit yesterday. Does the layperson in the audience really understand the difference between these two nuanced definitions? Probably not, right? But is it our responsibility as forensic scientists to represent it in an accurate way, to be knowledgeable about the statements that we make, especially in a court of law? I would think everyone would agree to say, yeah, I think that's the part that we're really responsible for.
And we've, someone commenting, is it wrong to say encompasses the range of results that could be reasonably attributed to the measurement? So it's actually the measurand. So the measurand is the true value in metrology speak. So the only change I would make to the statement is attributed to the measurand. So that's, the true value, but that's actually the textbook definition of measurement uncertainty, the range of results that could reasonably be attributed to the measurand.
So there's a question here that says, is it wrong to say that the measurement uncertainty encompasses the range of results that could be reasonably attributed to the measurement?
Yeah, that's what I just
Okay.
I was just talking about. But we've got plenty of people talking about also the analogies that they make, which is, I think, a very good pool of analogies if you want to look into that. We have on a balance or a train arriving or
Yeah, for sure. I think they've done great so far. I love seeing all the different examples that they've been given. And I think
the analogy of weighing yourself, I think is pretty common. Mm-hmm. It's a measurement that we're very comfortable with, and we expect that kind of variability. And it explains the variability that we expect from measurements really clearly. I think what's hard to explain sometimes about uncertainty is how this confidence interval represents the true concentration that we don't know, right? So Brigitte, you had shared with us some of how you guys represent uncertainty and how you help your toxicologists be prepared to explain this on the stand. Do you want to tell us a little bit about that?
Yeah, so we have this kind of a cheat sheet, 5x7 card that we've prepared for toxicologists, so they can just like easily slip it in their file when they go to court, and they have basically like the language that they can say and be sort of certain that it's the right language. So what we say is, the concentration of the report, it represents our best estimation, so it's the value best representing the true concentration in the sample as far as we know. And we have, when it comes to measurement uncertainty, we have good reasons to believe that the true concentration of the drug in blood or whatever is between the lower boundary and the upper boundary, since, for example, 95% of the time, the calculated interval contains the true concentration. And here, when we say 95% of the time, something that we tell our toxicologists when we train them is, when we say 95% of the time, what we mean is, if we were to do this 100 times, 95 confidence intervals would contain the true concentration. 5 of them would not. So if they're pressed on like, what do you mean by 95% of the time, then they can say, that if we were to do it 100 times, 95 of them would contain the true concentration.
Yeah, when I first read this statement and I see 95% of the time, the calculated interval contains the true concentration, I'm thinking 95% of the measurements and not 95% of the ranges that are established, right?
Yeah.
Which includes the measurement, but they communicate very different things, right? Or maybe not very different things. They communicate slightly different things. And this is where kind of that verbiage can be really tricky. In our lab, we use something much simpler, and it's not a stock standard. This is really kind of my personal preference, that we believe that the true concentration of that drug in blood or whatever is between the lower boundary and the upper boundary with 95% confidence. This to me is a very simple and true statement, that we convey the confidence without using any without suggesting any probability or any likelihood to confuse or misrepresent that, right? I think one of the questions that can come from this kind of presentation is going to be, well, is the lower boundary any more likely than the middle value, right? The center value. You said it's 10 plus or minus 2. We have a range of 8 to 12. Is 8 as likely the true value as 10? Or are they, dissimilar? So be prepared for that kind of conversation, right? And in that situation, what do you say to that? Is 8 more likely or less likely than 10, the actual value that was calculated or measured?
Well, I mean, yeah, what we always say is that the value we've measured is our best estimation, right? But we don't want to make likelihood statement of whether the lower bound is more likely than the upper bound, and sort of dive in the probability of these different values being true.
Yeah. Or another way to characterize it, maybe to say, I like that, recentering on the fact that this test measurement, this measurand, is our best estimate. And you can actually circle back to kind of that broader perspective of Emmy that we talked about, which is that inherently measurement processes have variance. And that's why we represented it in this way, right? To address and represent the variability that does take place in measurement processes.
Yeah, so I think you have a summary that kind of simplifies and distills everything down in terms of this particular topic. Your simply put slide, the next slide.
There we go. Sorry, I thought I had that up already.
No, you're fine. So, this can be a go-to or a new retooling for people to consider when they're discussing uncertainty measurement for the purposes of court, something that, is statistically correct. And I'm glad to see in the chat, I'm not the only person that may have had that mixed up just a little bit in my explanation as well. So that makes me feel good. We're gonna hit a couple of questions here from our chat before we dive into the next section. So the question was directed to Sue. They couldn't really remember which one of the sessions it was from, but the question is when you were talking about calculating the standard deviation of the sample, we wouldn't use the standard, oh, I'm sorry, that's the wrong one. Hold on a second. Small error on my part. Let me get it. That wasn't the one. Okay. Sue was talking about leaving in values that fell outside the expected range. This is part of calculating for your type A data for your measurement uncertainty. So leaving in values that fell out of the expected range. The question is how do you know when something is an outlier and needs to be excluded versus a value that was just out? Like, when does an out thing become an outlier?
Yeah, I think the question I would ask in return is, well, what are you using it for, right? Why do you need to know if it's an outlier or not? If we're talking about the monitoring of a method for its performance, we've established a QC acceptance criteria, right? Let's just keep it really simple. Let's say it's like from 4 to 6 nanograms per ml for this QC. Right, that's the predetermined. We use that criteria to say if the QC is between those two values, we have some additional assurance that the method is performing as expected. Okay, when you get a QC result that is 3 nanograms per ml, right? It's out of range, it's out of control. It tells us something that, hey, maybe your method is not performing as it should be. Now, when you're tracking QCs, for the sake of that batch, easy, right? Your QC failed, your lab has procedures for that. When you're looking at QC data for the sake of measurement uncertainty, let's say that's the end goal here that we're talking about. Do you throw out that point of 3? Well, it represents your method performance. It is probably the anomaly, right? Most of your values probably, hopefully, fall between 4 and 6, but occasionally they're out. They're 3.9, they're 6.2, whatever. And if they're out, they still represent the method as you would have values being produced during the normal course of the method, right? And so it still represents your method performance. Independent of that, your method has procedures to not report those results, but for the sake of measurement uncertainty, they should be kept in, right? It still is representative of your method performance. The topic of outliers comes up often because we're trying to figure out, like, well, what is an outlier and should I exclude it from my data set? And some of this comes from, you think about when you think about a, let's say like a research study, when we're talking about a group of, I don't know, let's say concentration of fentanyl in femoral blood for postmortem cases, right? Something like that, where you're trying to do a study and you're trying to say, does this sample represent the larger population? And that's what we're talking about. Is like, is that an outlier or
not? All right. Let's see. This is the question I started asking before. And when you were talking about calculating the standard deviation of the sample, wouldn't we use the standard deviation of the population and not sample? If we are using type A control data for every person in our whole lab system across the state?
Yeah, it's a great question. This is the exact terminology confusion that we talked about in session 2, right? Sample and population. What are we talking about? You're right in the understanding that you have that when you're describing every employee in your state lab system, you have a population, you have everybody in your lab system, right? And that part of this explanation is on point, right? You're not just testing Sue's QC samples, right? It's Sue's and RA's and Brigitte's, and we put them all together and it's representative of everyone. Now, what we're talking about, what I meant when I was describing that section, in that section, was talking about when we calculate the standard deviation of our QC material as a representation of the method performance, it's not the method performance every single time in every lab, in every situation for the end of time, right? There's no way to actually calculate that. And we only have a sample of our QCs, not to mention that QCs themselves are a good representation of, but not the actual measurement that you're making, right? The thing that we're reporting is not the QC result. The thing we're reporting is the concentration of something in an unknown. Brigitte, anything you want to add to that?
Well, no, I think you're describing it well, and yeah, I mean, it's always complicated, I think, especially in forensic toxicology, to have QCs that actually represent what you're measuring, because we have all of these different matrices that are sometimes, or often, I should say, complex, like postmortem blood and whatnot. And yeah, more often than not, it's going to the actual measurements are going to be more variable than what the QC does if you don't take great care, and even then.
Yeah, and I will add too that the distinction or the significance of those two different calculations is actually quite small if you have a lot of data points. Okay, so that you can have some peace of mind that helps you to understand that if you have 200 QC samples, you can do that calculation. You'll see it's actually very, very insignificant.
Yeah.
The reason, the situation where that's critical is going to be when you have small sample size. You can imagine how the different that's going to be if your n-1 is now 9 and not 199, right? That divisor really changes.
Yeah.
Nice.
Go ahead, Arya.
There's just one that I think we can knock out real quick. The question is, are these courses CMMI level 3 and ISO certificated? I'm not sure.
I'm going to say no because I don't know what CMMI stands for.
That's what I was thinking too. I was like, not this course, that's for sure.
But it is, I think they put it in the chat, FTCAE folks put it in the chat that it is approved for ABFT CE credit.
Yes, it is. That's great. Okay. If you want to, I want to make sure we get through a couple more of the slides that we already have prepared, because I feel like they're super valuable. So the next question, I think the next set of slides that we have are on the 2-sample t-test versus paired t-test, which was eye-opening for me as well. So thank you, Brigitte, again.
Yeah, so this is something I've barely touched on in my presentation, and I've had a couple of people reach out and ask about this. So when should I use 2-sample t-test? When should I use a paired t-test? So in both of these cases, you want to compare two sets of measurements, right? So we have measurement set A and measurement set B, and then we have some replicates of some kinds, I'm going to say, or different measurements in each set. And so the question you want to ask when deciding one test versus the other is, are the measurements that are, measurement 1 on your list, are they associated in a way that any other pair of measurements aren't? Okay, so this might seem a bit fuzzy right now. So if we go to the next slide, an example should help put that in place. Okay, so my first example is postmortem redistribution. So we have cardiac blood measurements, and we have femoral blood measurements, and we have the cardiac blood concentration in case 1 and femoral blood concentration in case 1, and then the same for case 2, 3, 4, etc. So if we ask the question that I posed on the next slide, so is cardiac blood case 1 concentration associated with femoral blood case 1 concentration? Are these associated? Well, yeah, clearly they're associated, and very strongly. Are they associated in a way that cardiac blood in case 4 and femoral blood in case 1 aren't associated? Well, yeah, I mean, in my measurements in case 1, cardiac blood and femoral blood, they're linked together, right? They're the same case. But if I take cardiac blood case 4 and femoral blood case 1, they're not tied together. So yes, we have an association, we have a paired, we have an association from line to line that exists, and in that case, yes, we should use a paired t-test. One example where we shouldn't use a paired t-test would be, for example, method comparison. So if I have a QC sample, I run it, X number of times, or 10 times on my LCMS method, and I run the same one QC sample 10 times on my GCMS method. So is replicate 1 LCMS associated with replicate 1 GCMS in a way that replicate 4 and LCMS and replicate 1 GCMS aren't? No, they're pretty much all interchangeable, right? If I were to randomize the list, they're not more associated the one with another on the different lines than they are with any other line on the other column. So this is a case where this is a 2 samples t-test that I should use, because there's no reason to pair replicate 1 with replicate 1 and replicate 2 with replicate 2 and so on. So that's how I would put the difference between 2 samples t-test versus pair t-test. But see, an example where the method comparison would warrant a pair t-test would be, for example, if I have LCMS results day 1 and the same QC run on the GCMS on the same day, and then I have, a week later a QC run on LCMS and the same day I run it on GCMS, then yeah, in that situation you have an association between, your lines in comparing your 2 methods. So
Brigitte,
so
what
you
about in the circumstance where you're bringing on a new assay, right? And you take all the samples from one batch and you run it on one instrument and you run the same samples on the other, right? So that's where you see the pairing take place. There's an association. It's actually the same physical sample run on both instruments. So it could be the same physical thing, or it could be some other kind of association that you're talking about, right? Day 1, the beginning of the run, they have that kind of relationship where they're not really independent of one another. Is that the distinction?
That's a good example as well. Yeah, if you were to run exactly the same batch on one instrument and exactly the same batch on the other instrument, then yeah, there's the pairing, there's an association between the 2 samples on each line.
Yeah, exactly. And I'm also seeing in the chat someone saying, yeah, or when you're comparing results from the same samples, right, before or after maintenance of instruments, same concept, right? It's the same sample, so those things are paired. They are, they're not independent. And so a paired t-test or a paired comparison is appropriate there.
Yeah.
Yeah.
Aria, I don't know if you had something planned, but I do want to also talk a little bit about the common misuses of statistics.
Yes, please. Let's go ahead and jump into that one. I'd love to get into the where does the plus or minus 20% stem from also before the end of this. We only have one panel question that's just about an opinion of scientific literature's overemphasis on p-value and significance. So if we have any time left, like maybe
that sort of folds right in the misuses of statistics.
Okay, well there we go. Perfect.
So yeah, that's one of the questions that had been raised by Sue in the hypothesis test webinar. So what are some of the misuses of statistics in forensic toxicology? And what I've seen throughout my career are some obvious mistakes where just people don't really know how to use the tools, and for example they flip the interpretation and they say, oh, I have a p-value of 0.8 and it's significant and there's a significant difference. Well, obviously you've just flipped the interpretation, and that's a obvious mistake, but when you don't know, you don't know. There's some clumsiness that occurs also. So if you use a paired t-test instead of 2 samples t-test, but I think that a lot of what I see as an issue is overestimating what statistics can do. And that's where the over-reliance on p-value that was brought up by the attendee comes up, right? Overestimating what statistics can do. So if you make some very strong conclusions in extremely small sample sizes without, bringing in the caveat that, okay, this relies on a limited sample and maybe there's further work to be done, or if you're testing hypotheses that make absolutely no sense on their face, and then you get a p-value and you're like, oh, this is significant, so my hypothesis is right, but it made no sense, no scientific sense to begin with, right? So it's a great thing that this attendee brought up, that this over reliance on p-value, right? So statistics is a tool in your bag, but it's not the end all be all, and you still need to be a scientist and make the science properly. And then statistics is there to sort of support your your scientific endeavors, but it doesn't, like, it won't correct all of your mistakes, and it still needs to be sort of used properly.
Which is
Right,
why we're
absolutely.
here. I'm trying to learn a little bit more so that we don't, put our foot in our mouth essentially and just stop saying things when we don't really completely understand them. So that's fantastic. And Sue, did you have a comment as well?
Yeah, I mean, I had a slide of this in my last presentation. We were so concerned of could I do it that we didn't stop and think, should I do it? Just
Yeah.
because you can get a p-value doesn't mean it means anything. And I think that's probably the biggest danger that we're in, is that, oh, but now I know how to do it in Excel. Then I'm going to do it, and then I'm going to get this p-value. I'm going to make some claims about it without really thinking about what did we just do? What was the data that went into it? Did I use that tool correctly? And so I think that's the kind of awareness that we were trying to do with this series, and to raise the general foundation of knowledge, so you ask the right questions before you start trying to, apply any of this knowledge.
Yeah, and I mean, sometimes the p-value is going to give you the wrong answer, right? There's an error rate to these, so again, it's one tool in your bag, but it's not the end all be all, and it's not going to solve all of your problems, unfortunately.
For sure. So this was one of my questions originally, which is going to be on the next slide, is where this plus or minus 20% came from. So it's a very interesting background, and I thank you guys for kind of diving into it. It's pretty generic, I think. So I'll let you take it away, Sue, if you want to start us off on that.
Yeah, sure. Brigitte, this reminds me of what you said earlier. You were asked this question enough times, you're like, all right, let's just get to the bottom of this. I've probably spent more than 10 hours of my life looking into this question, and I don't think I'm really at the bottom of it, but I do think I have more information than I had started with. So I'll try to keep it short. I'm sensitive of the time here. There's the answer to this question, where does plus or minus 20% come from? The question comes often, QC ranges are often plus or minus 20%. Where does that come from? It's a little bit of history, it's a little bit of statistics, it's a little bit of both, right? And I think the question that we really should be asking is, what should determine the QC range for a method? So when I talk about the history, what am I talking about? Thanks to Michael Wagner, who shared some of his experience with environmental tox and clinical tox with me. My experience has been exclusively in forensic tox. And so many of us asking that question have only lived in this world, right? In this world down here in forensic tox. So if we start with environmental tox, and at least in the US, the EPA methods are highly regulated. Okay, this is my limited understanding, having never worked in it. But part of that highly regulated environment includes standardized methods, and therefore standardized QC ranges. Some of these test methods, let's say, I'm making this up totally, let's say testing lead in soil, right, is a testing method that is often needed, and it's needed throughout the nation. And so these methods from all these different labs are studied in these round robin studies. Maybe some samples are sent to all of them and evaluated to ensure the robustness of this standardized test method. And what they did with that data was to evaluate it statistically, and lo and behold, 2 standard deviations was kind of represented by 20%. And so what they saw was that the variation of all of this data represented in all these different labs, right, actually ended up being that 2 standard deviations and 20% were kind of the same. And so the standardized methods and the standardized QC ranges adopted that 20% for those kinds of things, right? What we did in clinical toxicology and then forensic toxicology is to adopt that 20%, but do we stop and think about, like, what should it really be? And in forensic toxicology, we have 2 very different environments that address, that I think are relevant to this conversation. One is that we don't have standardized test methods that haven't been through this process, and that we are dealing with complex matrices. I don't know anything about dirt, so I can't speak to its complexity. But whole blood on its own has proteins and lipids and all kinds of things in it that make testing challenging, and where the reproducibility may not be so easily translatable from some other discipline. So I want to leave us enough time to kind of wrap up this conversation. If folks are interested in this conversation about this 20%, I think I'd be happy to chat about it more at STOF or at a future meeting. It is a really interesting story, but I think it's a question worth asking folks who have worked in other industries and other analytical sciences. And we may get some of our answers from some of those folks.
Well, thank you very much, Sue. And we're kind of wrapping up here, our last session, and I wanted to make sure that I had an opportunity to let my subject matter experts leave us with kind of their final thoughts. So, Brigitte, do you have some final thoughts for us before we sign off?
Sure. I mean, so we've discussed a bit the misuse of statistics, and I think one of the things I want to leave people with is that I understand your plight if you think, but I was coming in for answers and for like the right way to do things. And when I started, learning more about statistics, this is exactly what I had in mind. I was looking for certainty and for like, okay, this is the way to do it, and it's going to give me like for sure answers about my data, and that's what I was going for. And the more I went into details, the more I was like, oh, okay, so this is not the silver bullet that I thought it would be. There's a lot more nuance than I thought initially. And mind you, I mean, it's still important to know how to do it. Otherwise, we wouldn't be here for like 6 webinars talking about it. So it's still important to know how to do it, because what's the alternative, right? You throw your hands in the air and you go, well, whatever, I'm not analyzing my data. No, so it's still important to know how to do it, but it's important to understand that there are nuances to it, and that there are some very wrong things to do, but there's a lot of might be okay, and depends on your situation, depends on your data, and it's a tool in your bag, but don't forget to like see the whole forest. And as I said also in my presentation, a few weeks back, come back to it again and again. And, it's by being exposed to it and reading again and listening to it again that, things are going to fall into place at some point and are going to click. So, don't get discouraged if you think, oof, I'm not sure I understand everything. That's just normal. So that's, I think, what I want to leave people with.
That's great. Thank you so much, Brigitte. And Sue, did you have a few words for us?
Brigitte, you took the words out of my mouth. That's what this little graphic is for. If you're trying to go from here to here, and there are a lot of ways to do it. There really are. There's also a lot of ways not to do it. Like, that's not going to get you where you want to go. So it really was our hope with this series that we could maybe make that a little clear, and at least remove those like do not enter areas, and give you some tools to try to navigate this landscape a little better. And I shared this slide before, and I'll say it again, right? I hope like wherever you started on this journey with us, that you felt the progress from maybe one arena to the next, or at least progress in the right direction to ask more of the questions that you need to be asking, to maybe ask a more specific question, and maybe you've answered some of your own questions already. So in conclusion, I wanted to highlight that the website for this webinar series also includes lots of resources, and includes some free coursework, many of the resources, books, podcasts, and articles, anything that we thought was helpful as we were preparing this material. It is certainly available. And there is no replacement for taking a proper course. So there's no better time than now to take it or to retake it, pull out that textbook and revisit those concepts. That's it for me.
All right, great. That's about it. I just want to say, if you want to know what you don't know, try to put together a 40-minute talk on statistics and teach it to somebody else in your lab. You will find out very quickly where you're a little fuzzy right away. I just want to say thanks for joining us today for our final session, and thank you for RTI, David Heller and Brigitte and Sue, and all of you for joining us. Thank you very much.
As you depart, we kindly ask that you take a minute or two to complete our post-event questionnaire. The link will be pasted in the chat and also appear as you exit the Zoom room. Your feedback helps us improve our outreach efforts and continue to provide the best experience possible. Thank you again for attending, and we hope everyone has a great day.